Hello everyone, this is Reza Shokri from National University of Singapore, and I'm very excited about discussing our work on bypassing backdoor detection algorithms in deep learning, led by my former undergraduate student, Lester Tan. So this is about the vulnerability of machine learning algorithms, in particular deep learning to data poisoning attacks, where the attacker can poison the training set by adding some adversarial data that can change the way that the model represents and models the underlying distribution of the data. And as a result of that, changes the decision boundaries of the model that classifies data in different classes. This can lead to huge error on test data where the model is making misclassification due to this poisoning attack. The neural networks models have much more complex decision boundaries, and this would enable attackers to do some more complex attacks. In particular, they can run some targeted poisoning attacks instead of just trying to minimize the accuracy of the model. They can focus on a particular sub area in one corner of the distribution, add data points that have a particular common pattern and in one class, and label them as members of the other class and confuse the model so that the model would expand its decision boundary around them, would consider them as members of the wrong class. These attacks are known as backdoor attacks, and the particular features that they have are called the triggers of the backdoor. So the model actually is learning how to classify members of the blue class when they contain the trigger as members of the red class. So a couple of examples on this in face classification tasks. When you add the trigger, which in one case can be changing the input features, then the model wrongly classifies the input as some other class. And but this does not necessarily need to be the case all the time. The trigger could be also some latent features of the input. These are also known as semantic backdoors. For example, the inputs with white hair should trigger the backdoor and be classified according to the objective of the adversary. The backdoors are in general some type of exceptions in the decision-making process of the model, because for the data points that do not contain the backdoor trigger, the model looks at the features which are relevant for the task, but as soon as the trigger is present in the model, the model would prioritize that and would predict the label according to the objective of the attacker. So in order to maximize the accuracy of its predictions, the model would learn two representations of the data, one that is related to the backdoor trigger and the one that is related to the normal features of the data. This means that if you look at the latent representations of backdoor data and clean data, they are going to be distinguishable. And this is something that could be used to detect whether a data point is a backdoor or not. And this has been shown in many papers recently, and it has been used as the main idea behind detecting backdoor algorithms. But these do not consider the active attacks where the attacker can change his strategy to remain undetected. So the assumptions for those detection algorithms is that the attacker is only poisoning the training set with the poison data that contain the trigger. Whereas the attacker can actually change the training set and also change the model parameters such that the latent representations of the backdoor and the clean data are indistinguishable from each other. And here you can use adversarial networks with the objective of, one, being able to classify the data points correctly according to their label. Of course, the poisoning data are also present, so their labels should be predicted correctly as the adversary has labeled them. But in addition to that, we want to make the latent representations of backdoor and clean data in one class to be indistinguishable from each other. And here we use a discriminator network that helps achieving that at the same time as we are maximizing the loss over the labels. This would result in some representations of latent representations of the data which are not distinguishable from each other or not easily separable from each other, which would make it much harder for the detection algorithms to detect whether an input is a backdoor or not, or which neurons in the network are responsible for responding to the backdoor trigger. So if you look at in the static attack setting, where the attacker is only changing the training set and is not reacting to the detection algorithm, these techniques are pretty accurate. So they can prune the neurons which are responsible for the backdoors without damaging the accuracy of the model. However, in the case of an adaptive attack, where we have maximized the indistinguishability between the latent representations of backdoor and clean data, the detection algorithm would make a significant amount of error. Number one, as you see, it's not able to detect which neurons are connected to the backdoor task. So the attack accuracy remains high, but as they are pruning, they have a high false positive error. So they prune the neurons that are responsible for the classification task. And by pruning more of those, the accuracy of the model on the clean data decreases. Also, there are these algorithms that try to detect whether the input is a backdoor input, which is the input that contains the trigger. And in the static attack setting, where the model is poisoned with the data, then you see that majority of the poisoning data are removed. Almost 90% of the data points are removed, however, or detected. However, in the adaptive setting, the majority of backdoor data remain undetected. So there is also a false positive in this case, where many data points which are clean and do not contain the backdoor trigger would be selected or detected as falsely as a backdoor input. So in general, as we see, using adversarial backdoor embedding as an adaptive attack against backdoor detection algorithms would prevent them to perform accurately. They have huge error rates, and the attack remains undetected. So this, in general, for the detection of the backdoors, or for training models which are robust against backdoor attacks, this paper calls for a more systematic formalization of the problem, having a formal definition for backdoors, for which we can prove that the model removes them or basically is robust against the attacks. So that is needed. Also, in general, especially in the case of designing defense algorithms in machine learning, we would need to assume adaptive attackers in order to be robust against the attackers in the worst case scenarios. More information could be found on my website, and I hope that you enjoyed reading the paper.